Welcome to this short introductory presentation about low-energy ion scattering, often referred to as LEIS. In today's presentation we will discuss sample preparation. LEIS is known for its ultimate surface sensitivity, allowing you to quantitatively determine the elemental composition of the outermost atomic layer. Noble gas ions are scattered from this outer atomic layer, and the energy loss in these scattering events is used to identify the elements in the surface. To do this, the outer layer has to be available to the ion beam and not covered by contamination. However, after transport through air, most samples are covered by 1 to 2 nanometers of adsorbed hydrocarbons. How do we solve this problem? Even if the surface is not contaminated, it ideally has to be in the same chemical state that it is during its application. For heterogeneous catalysts, this state strongly depends on the chemical and physical conditions. Depending on the sample, a cleaning method is chosen from a range of options. The most commonly used method is atomic oxygen treatment, which will be discussed in more detail shortly. Alternatively, the sample can be heated in ultra-high vacuum or any inert and even some reactive gases like oxygen and hydrogen. In the QTAC 100, temperatures of 900 degrees C can be reached in UHV and up to 600 degrees C in gas, depending on the gas and the pressure. This allows one to evaporate or convert the hydrocarbons to volatile species which are pumped away. More importantly, especially for catalyst applications, is the ability to bring the surface into the desired chemical state. For example, the working state of a catalyst using well-controlled heating and gas treatment. By rapid cooling of the sample to room temperature, the state can be preserved and subsequently analyzed. Many other sample preparation techniques can be adapted to the pre-chamber of the QTAC 100. For example, sample cleavage to expose fresh surfaces of glass or other materials in vacuum. Also, thin film deposition can be performed to prevent an air break between deposition and analysis. Ultimately, the instrument can be coupled to deposition systems or other instruments to form an integrated cluster tool. The aforementioned atomic oxygen treatment is standard for many samples. In the OH source, a low-power oxygen plasma is run in a confined volume, creating oxygen radicals. These atoms flow with a stream of oxygen from the plasma chamber to the surface of the sample, while the charged particles are held back by an array of apertures. This prevents any energetic particles from the plasma reaching the surface. Therefore, only thermal energy oxygen atoms reach the surface and no sputtering occurs. The plasma is fully separated from the sample. Atomic oxygen has a very high ability to oxidize on contact with matter. Therefore, any hydrocarbons on the surface will be attacked and converted into small volatile molecules. Inorganic contamination, as well as the surface itself, is oxidized into the highest oxidation state. This usually only occurs in the outer layer, as this room temperature process usually does not transport the oxygen into deeper layers. As the sample is originally transported through air, it will already be oxidized, so the atomic oxygen exposure will not change the outer surface. Atomic hydrogen works in a similar way, but will reduce the surface, although usually not completely, at least at room temperature. This plot was created by measuring the thickness of self-assembled monolayers on gold after increasing duration of atomic oxygen exposure. It shows that after a short transient, the cleaning speed on this material is on the order of 1 nanometer every 10 minutes. In practice, cleaning of adsorbed and less ordered hydrocarbons is usually complete after 5 to 10 minutes. This figure illustrates the effect of atomic oxygen cleaning. A copper oxide thin film on silicon was measured as is, and after 10 minutes of atomic oxygen cleaning. Before the cleaning, only carbon and oxygen peaks are visible in the black spectrum. Hydrocarbons usually expose hydrogen to the surface, which cannot be detected in LEIS. After the cleaning, the red spectrum shows strong copper and oxygen peaks, besides phosphorus, which is a contamination from the deposition process. Sample preparation is a natural part of working with LEIS, as the ultimate surface sensitivity requires the analyst to bring the surface into the relevant state. This includes the removal of atmospheric contamination, but also the preparation of the surface to represent the surface of interest under practical conditions. For this, the QTAC 100 has a wide range of options which can be attached to the pre-chamber. The atomic oxygen source is almost always installed, as it is applicable to a large fraction of samples. For more information, please visit www.iontoff.com/QTAC.